chapter 25.5. This is the field model. So the first thing we've done so far is to look at the forces between charged particles, and we explained that by using Coulomb's law. Since we've said that the force involved is a non-contact force, meaning it's an action at a distance force, it means that there is some sort of something going on there which allows the two charged particles to exert forces on each other, and that's where the concept of a field comes in. So the idea of the field is that a particular charge distorts the area around it. Okay, so the concept of field means the field is a distortion of the area around a charge. Okay, so we can say that we can explain the interaction by using a field model. We can say that the field is a distortion of the space around a charge, and we call this distortion an electric field. So we shall use the symbol E for electric field. The field, of course, is a vector quantity. So we know what that means. It means it has both magnitude and direction. Okay. So if we put a charge at some point in space, we shall call this charge a test charge. No, sorry, a source. We call this charge Q a source charge. So this is the charge Q. So it's a source charge, and so it produces a distortion of the space around it. So if we put a charge at some point P, if we put another charge, let's call it Q subscript T, so we shall say it's a test charge. If we put it at that point P, if it's a positive charge, it will experience a force this way. So this is the force of the source on the test. So let's do it this way instead. So this is the force of the source charge on the test charge. So we are saying that the test charge experiences a force because it is in the field of the source charge. Okay, the source charge is Q, and the test charge is Q subscript T, and if you place it at a certain point P, it experiences a force. Okay, so this allows us to define the electric field. So we define the electric field E at the point P as follows. So we know that the source produces a certain field around it which interacts with the test charge, exerting a force on the test charge. So we can say the electric field at the point P due to the source charge is equal to the force on the probe or the test charge, force on Q subscript T divided by the test charge Q subscript T. So it is a force per unit test charge. So the electric field is a force on a test charge at some point in the space. So the electric field at the point P is the force, the test charge. So in 3 dimensions, the electric field at P, X, Y, Z is equal to the force on the charge at that point divided by the test charge Q subscript T. So force on the test charge Qt at that point divided by the test charge. We already know the force on the test charge from Coulomb's law already. So the force on that charge is equal to K Q source Q test divided by R squared, where R is the distance between from the source to the point. So R is the distance between the source charge and the test charge. So then we can say that the electric field at P is then equal to K Q for the source, Q for the test, divided by R squared times 1 over Q for the test charge. So we can cross out the test charges, and we shall have the electric field at the point P to be equal to K Q for the source charge times R squared, where R is the distance between the source and the test charge. Since the electric field is a vector, and we can use a unit vector notation and put this as R hat, where R hat is the direction along R. Okay, so we have our source charge Q at some point in space. The distance to the point P is given by R, and so at this point there's an electric field E at the point P, which is given by K Q over R squared, and R hat is unit normal vector divided by R, so it's this distance here. Okay, so it just tells us that the electric field is radially directed, where R is the direction along, where R hat, this is R hat, is the direction along R. So the electric field moves radially from the point charge. So this just tells us that if we put a certain positive source charge in space, we can say that the field goes away from it this way, and as you get further away, if you can think of various points along those arrows, the farther you get away, the shorter the arrow becomes. And so if you put a probe or the test charge at some point in that electric field, it experiences an electric force according to Coulomb's law. So we define the electric field as a force per unit test charge, or the force on the unit test charge at that point in space. The electric field exists in space whether the test charge is there or not. So the electric field is there whether the test charge. Okay, so the electric field is not due to the presence of the test charge. It's there whether a test charge is there or not. You can know the electric field is there if you put a test charge at that location. Then it will experience a force. So that tells you there's an electric field at that point in space. We can do this for a negative source charge also, and we shall have the same result. So we can say that, is everybody done writing? So we can say that suppose we use a negative source charge. So suppose we use a negative source charge, we have this. So let's say we have a negative source charge, let's call it Q, at some point in space. So if we go to a certain point P in the space around that source charge, if we bring a probe, a test charge, which is a positive test charge Q, to that point, it will experience a force that way, going towards the negative source. Okay, and so if our distance between those two is R, then we can say the electric field at that point P, due to the negative source charge, is going to be equal to K Q for the source charge divided by R squared, where Q is negative source charge. Okay, so you can see the electric field, again, we're using the magnitude. Okay, we can use the magnitude. So the electric field is just equal to KQ over R squared. If I put the source as negative 5 microcoulombs, then E is equal to K magnitude of 5, or magnitude of negative 5, which is equal to 5. So the electric field is going to be the same. The only difference is that if you have two charges, one of them is a positive source charge plus 5 microcoulombs. One is a negative source charge minus 5 microcoulombs. If you put a probe at some point P in space, which is the same distance from them, it will experience the same force, Coulomb's law. So it experiences the same electric field at that point. The only difference is that one of those charges will be attracted and one of them is repelled. Okay, because one of them is positive and one is negative. So the negative source charge attracts the positive probe, and the positive source charge repels the positive probe. But the magnitude of the electric field is the same at that point in space. Okay, so we can say that for a negative charge in space, the electric field goes towards that charge like that. And the same thing applies if you think of various probes at different points. The farther you are away from the charge, the smaller the electric field is going to be. It goes as 1 over R squared. Okay, so we shall go on to the electric field model next, or electric field next. So let's continue. So this is now chapter 26. So we've already seen what happens when you put a probe or test charge at some point next to a source charge. The source charge has a space around it, distorts the electric field around it, and so it produces an electric field which acts on the test charge. So the electric field is the force on the test charge divided by the test charge. That's what gives us our formula. So let's go on to look at the electric field of multiple charges. So we can say that if we have multiple charges at some point in space, or we have multiple charges. Hold on a second. Suppose if we have multiple charges, we can find the electric field due to these charges at some point. So we'll do that next. Let me make sure that I have everything I need. So let's say we have several charges. I'll put several charges here, and we have a certain point P in space. We want to find the electric field due to these charges. Let's say this is Q1, Q2, Q3, all the way to say Qn. So we can say that the electric field at that point P, we're using the vector notation, is equal to the electric field due to the source charge 1 at P plus the field due to the charge 2 at P plus field due to charge N at P. So that would be the electric field at P due to the various charges that we have there. And we can put it into the component form. We can say that the x component of the electric field at P is equal to the x component of the field from 1 at P plus the x component from the field from 2 at P plus the x component of the field from N at P. And in the same way, we can find, so this can be written as the sum from 1 to N of E subscript I Px, something like that. E subscript I Px. I at P in the x direction. So this is I goes from 1 to N, and the electric field, the y component of the electric field at P is equal to the component of 1 in the y direction at P plus the component of 2 in the y direction at P plus the component of N in the y direction at P, which can be written as the sum from I going from 1 to N of E subscript I Py. And we can do the same for the Z component also. Since we're working in 3 dimensions, let's do that then. So we can say that the Z component at P, the electric field in the Z direction at P is going to be the field from 1 at P in the Z direction plus the field from 2 at P in the Z direction all the way from the field from N at P in the Z direction. So this is the same way we can do. Actually, maybe let's do it this way. Yeah, I guess the I is fine. We can use I. It's fine. The electric field from I1 to N of E, I, P, and Z. Okay. And so the net electric field is just a sum of those electric fields. So the net electric field at P is equal to the electric fields that we've just done, the net electric field. So it's going to be Ex at P plus Ey at P plus Ez at P. So this is the principle of superposition, as we've said before, principle of superposition. So we can do one example, and then we'll go from there. So let's try an example. So we can have a source charge at some point in space. So this we can say is A. This is the point 1, and this is 2. This is also A, and this is a source charge here. So we're finding the electric field at the points 1 and 2. So A is equal to 0.1 meters, and the source charge Q is equal to 5 microcoulombs. So I want you to find the electric field at the point 1 and the electric field at the point 2. And the hint, of course, don't forget that there's a distance between them. So you're going to use the distances. So electric field at this point and that point. Okay. This is a positive source charge. So the field at the point 1 and 2 will point away from the electric field. So this would be E1 and this would be E2. So that use the definition of the electric field at a point in space to calculate the electric field at E1 and the electric field at E2.
E1 is 4.5 meters.
Okay, give me a second. So you said E1 is what? 4.5 times, and this is newtons per coulomb. I should have mentioned earlier that the unit of the electric field is newtons per coulomb, but I'll point that out at the end. Okay, so the other one is 3.9. What else do you have? 10 to the power. So those are the answers we have. Is anyone getting a different answer? What? The answer E1 is 4.5 times 10 to the power 6. newtons per coulomb, and E2 is 3.9 times 10 to the power 6. That's the answer. Okay, so let's check it and see. So E1 is equal to KQ over the distance A squared. So K is 9 times 10 to the power 9 times 5 times 10 to negative 6 divided by A, which is 0.1 squared. Okay, and what does that give us? Times 10 to what? 6. Okay, newtons per coulomb. 4.5 times 10 to the power 6. And then E2 is given by K times Q divided by the distance. Then what would the distance be? So it's going to be A root 2 again. So 0.141, something like that, squared. So this is going to be 9 times 10 to the power 9 times 5 times 10 to negative 6 divided by 0.141 squared. And what was the answer? So how did you get 3.9? Seems like people are getting 2.3 times 10 to 6. Did you use the A root 2 for that distance? I guess not.
Because the first one is 0.1, and then the next one is
0.14.
0.14 squared.
Yes.
Yeah, and I got.
Okay. So we'll say that 2.3 times 10 to 6 is correct, and 4.5 times 10 to 6. So those are the two electric fields. Okay. Let me just add that the unit of the electric field, I should have said this earlier, but better late than never. So we said the electric field was defined. So we said from the definition, so E is equal to the force per unit test charge. So this is force in newtons, charge in coulombs. So unit of the electric field is Newton per coulomb. So I want to do one more example on this when we come back on Thursday before we get into continuous charge distributions. So we'll leave this here. It's almost 7:30, so we'll stop here and go and do the lab on electric fields. When we come on Thursday, we shall do another example on two charges. This time I'm going to do the example on electric dipole. Okay, and so once we do the electric dipole, we'll go on to the field of a continuous charge distribution. All right, so let's stop here. I'm going to save this.